Okay, so today what we want to look at is interpreting values in our least squares regression equation, and also the concepts of interpolation and extrapolation, which I did touch on when I introduced the least squares regression line in that graphing package in our last video, but we'll have a look at that in a bit more detail. So the first thing is being able to interpret the values of the slope and the y-intercept of our regression line in the context of the problem that we're dealing with. Okay. Now again, we can construct some reasonably formulaic sentences that you can use, but more and more VCA are trying to find ways to give you data variables that make that harder to be formulaic about. So we'll try and look at some slightly different ways that we can explain or interpret the slope and the y-intercept of the regression line. Okay, so in the last video we did an example where we looked at the relationship between the height in centimetres of plants and the hours of daylight that they're exposed to. And we established the following regression equation. Plant height was equal to 28 plus 1.5 times hours of daylight. So in this instance, A, which is the y-intercept, is 28, and B, which is the gradient or the slope, is 1.5. And the interpretation of those values would be as follows. Okay, if we know the gradient is 1.5, so this is about understanding of what gradient is. A line with a gradient of 1.5 means that for every one step across, sorry, I should have drawn a slightly steeper line than that. So for every one step across, it goes 1.5 up. That's what a gradient of 1.5 means. So we want to be able to interpret that in the context of across is the x variable, so hours of daylight. So 1 hour of daylight is connected to 1.5 centimetres of height of the plants. Okay, is essentially what our gradient is telling us. Okay, so for every 1 hour increase in daylight that the plant is exposed to, the plant would be expected to grow an additional 1.5 centimetres in height. So the sentence I've got written here is, on average, plants are expected to grow 1.5 centimetres for every additional hour of daylight they are exposed to. Okay, so it's really important that you make reference to units that are specific to the question. Okay, and that you really relate it to the variables in question. It's also important that you're a bit vague. Okay, remember this is a prediction. It's based on a line of best fit. It's not saying that every time you get an extra hour of daylight, the plant will grow by 1.5 extra centimetres. Okay, that is the implication, but it's on average. It is, we would expect that this might happen, we would predict that this might happen, okay, not that this will happen. So it's really important that your language stays suitably vague. So the sentence I've used here is, on average, plants are expected to grow 1.5 centimetres for every additional hour of daylight they are exposed to. Okay, it's really important. So you'll notice I've said additional hour. It's really important that there's a sense of, as the x variable increases by 1, the y variable increases by whatever, or decreases by whatever if you've got negative gradient. Okay, so we might also say, another way we could say this would be, on average, for every 1 hour increase of daylight that the plant is exposed to, it can be expected to grow by an additional 1.5 centimetres. Okay, but it's really important there's a sense of, so grow 1.5 centimetres means increase by 1.5, additional hour means increase by 1. So for every increase by 1 in that variable, we're getting an increase by 1.5 in that variable. Okay, those things are really, really important. The second sentence, the interpretation of the y-intercept. So remembering the y-intercept, let me just get rid of this area over here so I can draw here. So remembering the y-intercept, we've got our scatter plot, we've got this is our hours of daylight, this is our height in centimetres. Okay, so the y-intercept of a line is this point here, okay, where the line crosses the y-axis. So we're seeing that it's crossing at a y value of 28, or in this case a height of 28. So what that means is, it is when our x value is 0, our y value is whatever the y-intercept is. when our explanatory variable is 0, the response variable will be equal to whatever the y-intercept is. Okay, so in this particular situation, the sentence I've written here is on average. So again, keeping it nice and vague. It's not saying that every plant that's exposed to 0 hours of daylight will grow to this height. It's a on average, we would predict, etc. And we'll talk a bit more about the fact that the validity of this prediction might not be great because technically it's an extrapolation. But on average, a plant exposed to 0 hours of daylight can be expected to grow to a height of 28 centimetres. Okay, so again, can be expected to, would be predicted to, will grow to an approximate height of, okay, appropriately vague language. Good to start with on average, okay, on average, not all the time, but the line says that on average this is what should happen, okay. Alright, let's have a look at another example. Relationship between average temperature and latitude is considered and found to be described by the following regression equation. Okay, we'll talk more about latitude in the geometry module later on in the year. So latitude being sort of the distance away from the equator. So obviously, the further we get away from the equator, the less and less the average temperature gets. Okay. So in this instance, average temperature is 43.0 minus 0.9 times the latitude. So here our A value, our y-intercept is 43, and our B value, our gradient, is negative 0.9. So these values could be interpreted as follows. On average, the temperature is expected to decrease by 0.9 degrees Celsius for every 1 degree increase in latitude. Okay, so it's again, how does the response variable change compared to the explanatory variable? So the response variable decreases by 0.9 every time the explanatory variable increases by 1. That's what our gradient is telling us. Negative gradient means the response is going down as the explanatory goes up, and it's going down by 0.9 for every 1 change in the explanatory variable. So on average, the average temperature is expected to decrease by 0.9 degrees Celsius for every 1 degree increase in latitude. Again, you can restructure that sentence. On average, for every 1 degree increase in latitude, we can expect the average temperature to decrease by 0.9 degrees Celsius. Okay, again, including units, degrees Celsius, degree, latitude is also measured in degrees, different kind of degrees, but making sure we're including units and information specific to the variables in the question. The y-intercept tells us that at a latitude of 0 degrees, when our explanatory variable is 0, when latitude is 0, i.e. that's on the equator, the average temperature is predicted to be approximately 43 degrees Celsius. Okay, again, predicted to be, not that it will be. You could say expected to be, it will be approximately. Okay, so you just want to make sure you're using that sort of vague language. And again, you probably want to try and say on average. So you might say on average, or usually, or the line predicts that at a latitude of 0 degrees, the average temperature is approximately 43 degrees Celsius. Okay. Yet another example, relationship between the number of runs made and the number of balls faced by a batsman in a cricket match is explored. The equation of the least squares regression line is found to be this. Okay, so the number of runs scored is negative 2.6, that's my y-intercept, my A value, times 0.73, that's my slope or my gradient, times the number of balls faced. Okay, so these values can be interpreted as follows. So the gradient, okay, on average for every 1 ball faced, batsmen in this game made approximately 0.73 runs. Okay, on average, approximately. Okay, again, for every 1 ball faced. So as the number of balls faced increases by 1, the number of runs gained increases by 0.73. Okay, but again, you can use language specific to the context. On average, for every 1 ball faced. That means every time a player faces 1 ball. Okay, so adding on 1 to the number of balls faced. A batsman in this game made approximately 0.673 runs. So making a run, the implication is increase, okay? But that's specific to this particular context. So increasing the number of balls by 1 increases the number of runs by 0.73. On average, approximately, etc., etc. Now, the y-intercept here is interesting. On average, a batsman who faces no balls, okay, so when the explanatory variable is 0, number of balls faced is 0, we're getting the number of runs that would be made. So that's what the Y-intercept is telling us. So on average, a batsman who faces no balls can be expected to make negative 2.6 runs. Now obviously in this particular example, the Y-intercept doesn't make sense. And we can talk about that a bit further on. It's because it's an extrapolation away from the data. And in fact, the line of best fit is only relevant within the range of the data. So we've extrapolated too far away from the range of the data here, and actually it's meaningless, okay? And that's because obviously in this particular game or this data set from which this regression line was taken, every batsman had to face at least one ball, but they obviously all faced, you know, a couple of balls, so that the data set was a bit away from. So what you're seeing here is, let's say you've got your scatter plot and you've got balls faced on the horizontal axis and runs on the vertical axis. So your data set's sort of here, okay? That's what's happening. So the number of, you know, when someone faced, I don't know, I'm making numbers up, 5 balls, they made 1 run, okay? Let's say that's the lowest data point. And then things go quite steeply. Now, if you fit a line of best fit to this data, you're going to get a negative Y value, okay? But the point is that the line of best fit is only really relevant in this range here where the data actually is. And out here, this is a very big, we call that an extrapolation. It's away from the data set and it's actually pretty meaningless. So we wouldn't be asked to interpret the Y value, the Y-intercept in this particular question, because it's actually a little bit meaningless. We need it in order to actually draw the line of best fit so we can be making good predictions in this area, but we wouldn't be making predictions down here when the X value is 0, when the number of balls faced is 0. Okay, so as I said, this leads us on to thinking about that interpolation and extrapolation, which we'll talk about over the page. This can happen if we've only got quite a small data set, which this would be a small data set. We can often get a Y value that's a bit meaningless, or it can also be that the model's only valid within a particular range of X values, and that could also be true in this instance. Alright, so I'm going to try to generalize the sentences, but I really want you to start to learn to be a bit flexible about these sentences. But I want you to keep your language suitably vague. I want you to use phrases like on average, it's predicted to, it's expected to, it's approximately, okay? So that you're not saying that this will definitely happen. So generalized interpretations, A gives the approximation for the response variable when the explanatory variable is 0. And on average, B gives the predicted average increase or decrease in the response variable when the explanatory variable is increased by 1 unit. So if B is positive, we've got positive gradient, the response variable will increase as the explanatory variable increases. If B is negative, we've got negative gradient, the response variable is decreasing as the explanatory variable increases. My apologies. Okay. So let's have a look at this. In a group of newborn monkeys were studied and their average height in centimetres was calculated at monthly intervals. The regression equation is found to be height equals 12.1 plus 3.5 times the number of months since birth. Interpret the slope and the Y-intercept. Okay, so the slope in this instance is 3.5. Okay, and so what that is telling us is that for every 1 unit of increase in the explanatory variable in the number of months, we get on average a 3.5 unit increase in this case, the response variable, which is height. Okay, so each month, on average, so for every 1 month increase, the height of the monkey, of the newborn monkeys, increases by approximately 3.5 centimetres. On average each month, so for every 1 month increase since birth, the height of the newborn monkeys increases by approximately 3.5 centimetres. Okay, interpretation of the Y-intercept. So the Y-intercept is 12.1, and remember the Y-intercept is giving us the value of the response variable when the explanatory variable is 0. So the value of the height when the number of months is 0. Number of months since birth is 0, means at birth. Okay, so what we're suggesting here is that on average, at birth, which is when the response variable is 0, the explanatory variable is 0, the height of a newborn monkey is approximately 12.1 centimetres. So on average, at birth, that is when the number of months since birth is 0, the height of a newborn monkey is approximately 12.1 centimetres. Using the regression line to make predictions, okay, so once we've got our regression equation, the whole point is then being able to make prediction, but we need to be a bit careful about how we do that, okay? So we're trying to predict the value of the response variable from the explanatory variable. It should be noted that the regression line is only an estimate of the true relationship. Okay, remember it's a line of best fit, it's not actually going through all the data points, so it's an estimate of the relationship between bivariate data. The coefficient of determination tells us how confident we can be in that estimate. Okay, so it gives us a measure of the predictive power of a regression equation. So for example, the regression equation for the growing monkey, which we had on the previous page, has a coefficient of determination of 0.987. So that means we can be 98.7% confident in our predictions. Okay, 98.7% of the variation of the monkey's height can be explained by the variation in its age in months. Okay, so in this case, the regression equation has highly significant predictive power. We can be pretty confident about the predictions we make using this particular regression equation. So level of confidence is definitely going to be to do with the strength of the association, but the other thing we need to be a bit careful about is whether we are interpolating or extrapolating from the data. Okay, so there's two types of prediction. Interpolation is when we make a prediction within the range of the data. Okay, so we can see that this data is based on actual measured heights from 1 to 6 months of age. So if we make a prediction for the height of a monkey at 2.5 months, that's an interpolation. That's within this range of data. If I wanted to use this model to make a prediction of the height of the monkey after 3 years, so 36 months, that would be an extrapolation. And it's a long way away from this particular data set on which we're basing our regression equation, and therefore we would have to be a bit skeptical about the accuracy of that prediction. Okay, so if we were using a regression equation to predict the height of a monkey at age 4.5 months, that's an example of interpolation. 4.5 months is in here within the data set. If we were going to make a prediction at 8 months, it would be an example of extrapolation. Now, 8 months isn't far from the data set, so even though it's an extrapolation, we might still be able to be reasonably confident in the prediction. However, if we wanted to make a prediction, as I said, at 36 months, I wouldn't be very confident about that prediction on the basis of the height of the monkey from 1 to 6 months. Okay. So in general, we can expect predictions made through interpolation to be reliable, particularly for high coefficient of determination. Predictions made through extrapolation are less reliable. That is that we don't really have a way of knowing if they're reliable or not. Okay, even if we have a high coefficient of determination. Okay, because the data could change very significantly after that. Perhaps it's linear within this range and then it's non-linear at all and it really drops away or something changes, and so therefore our linear model becomes irrelevant outside of this data set. So generally speaking, when you've got questions in a test or an exam that ask you about the reliability of the prediction, they're probably looking for you to make reference to whether the prediction is an interpolation or an extrapolation. Now, using our CAS to make predictions using the regression equation. Now, I'm not going to go into this. For those of you that study maths methods or who did maths methods last year possibly and are reasonably comfortable with function notation, it can be quite quick and efficient in your CAS to make use of that function notation. I'm not going to go through this for everybody, but there's details there about how you can use the function to therefore be able to quickly and efficiently make prediction. Alright, so let's have a look at an example here. Growth of a sample of newborn snakes was studied. Their lengths were measured at regular intervals and an average length calculated. Identify the response and explanatory variables. Okay, so here we're looking for the explanatory variable to be the age in months, and therefore the response variable in response to the age, we're looking at the length of the snake in centimetres. Find the equation of the least squares regression line in terms of age and length, giving all values correct to 3 significant figures. Okay, so I've got a new document here. I'm going to insert Control I, a lists and spreadsheets page. Sorry. Control I, a lists and spreadsheets page. Okay, and then I'm going to put my data set in here. So I'm going to name my columns. So we have age and we have length. Okay, and then I'm going to put the data in. So age after 1, 3, 5, 8, 12 and 18 months has been measured. Again, the errors you'll make in these questions will be in not taking care with your data entry, so really do take the time to put it in right. It will make life easier in the long run. 48, 60, 71, 93, 117, and 159. Okay, so there's our data set. So we need our regression equation. So menu 414. Our X list, the X list, sorry, is age, and our Y list is length. Our response variable. Tabbing down to the bottom here. Now we don't want the results in column B. We've got data in column B, so we want the results in column C. Okay. Alright, so here we've got our regression equation information. We want to write the equation in terms of age and length. Okay, so remembering age is our X variable and length is our Y variable. So our equation is Y equals A plus BX. So Y is length. So length equals A. Now we want 3 significant figures. So our A value is 40.1 to 3 significant figures. Plus our gradient to 3 significant figures, which is 6.54 multiplied by x, which in this case is age. So length of the snake is equal to 40.1 plus 6.54 times age. Interpret the values of the slope and the y-intercept in the context of the data. Okay, so slope is 6.54. So that is for every 1 unit increase in age, we're getting a 6.54 increase in length. Okay, so as the snake, for every 1 month, okay, for every 1 month in age, as the snake's age increases by 1 month, its length can be expected to increase by approximately 6.54 centimeters. Okay, so on average, for every 1 month increase in age, the snake's length is expected to increase by approximately 6.54 centimeters. Y-intercept is 40.1, so that says on average, when the age is 0, so that is when the snake is born, at birth, a snake's length is approximately 40.1 centimeters. Okay, part D. Use the regression equation to predict, correct to 1 decimal place, the length of a snake at age 6 months. Could this prediction be considered reliable? Why or why not? Okay, so let's make the prediction first. Alright, so we want predicted length. Oops, sorry. So predicted length, our length equation is 40.1 plus 6.54 multiplied by age. Now we want age in months and we want age at 6 months. Okay, so I'm going to need a calculator page. So if you haven't already got one, Control I to insert a calculator page. My page 1 in this document is a calculator page, so I'm going to press Control left to tab across to that, and I'm going to do 40.1 plus 6.54 times 6. Okay, so predicted length is approximately 79.34 centimeters after 6 months. For those of you that did read through that function notation information and want to have a go at that, when you did your regression equation, your CAS saved the regression equation as f1, okay? So f1 of x, if I type into the calculator screen, there's the regression equation. The advantage here is that the gradient and y-intercept aren't rounded at all. So if you want to substitute 6 into that equation, f1 of 6, okay, 79.34. The questions in Further Maths will be designed so that there shouldn't be any rounding issue depending on whether you use the rounded equation or the exact equation. Okay, you certainly won't be penalised for using an exact equation. Okay, so the predicted length of the snake after 6 months is 79.34 centimetres. The next part of the question says, could this prediction be considered reliable? Why or why not? Reliability, that needs to flag for you, that's about interpolation, extrapolation. Okay, so 6 months is within the range of the data set. The data set goes from 1 month to 18 months. 6 months is somewhere in here, and so that's an interpolation. And so therefore the prediction should be pretty reliable. Apologies, I don't know why that keeps opening. Okay, so this prediction is an interpolation. Hence, it can be considered reliable. Let's just have a quick look. Let me go back over to my regression in my CAS. We've also got coefficient of determination of 0.99, so almost 100% certainty. So actually this is a very, very strong prediction. Prediction is an interpolation, sorry, very accurate prediction. Hence, it can be considered reliable. So you've got a strong association within that range of values. So an interpolation with such a strong association is certainly a reliable prediction. Use the regression equation to predict the length, correct to 1 decimal place, of a snake at age 24 months. Okay, so again, predicted length, 40.1 plus 6.54 times the number of months, which is 24. Okay, over in my CAS. So again, rather than retyping it, I can scroll back up to the calculation I did previously, press enter to copy it down, and just edit the 6 months to change it to 24 months. Okay, again, you want to look to be efficient if you can. Correct to 1 decimal place. Now, I got my previous question wrong because it was correct to 1 decimal place, so it should have been 79.3 centimetres, the previous question. Correct to 1 decimal place here is 197 point. Now, that's okay. Just be a bit careful about that, but yeah. 197.1 centimetres to 1 decimal place. So again, if you used your function definition with your CAS and you did f1 of 24 and rounded that to 1 decimal place, it is still 179.1. Could this prediction be considered reliable? Why or why not? Okay, now predicting at 24 months, the data set goes from 1 month to 18 months. So 24 months is an extrapolation, and so therefore we would need to be careful about the reliability of this prediction. Okay, so this prediction may not be reliable because it is a result of extrapolation. Sorry, try that again. Extrapolation. Okay, so again, reliability, generally we're looking for you to use the word interpolation or extrapolation to draw a conclusion, and that's how we make use of our least squares regression line to make prediction.